Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing the probabilistic method. What is the probabilistic method? Roughly speaking, the probabilistic method is the use of randomness to prove the existence of combinatorial objects. It's one of the most important methods in combinatorics, and we'll be going over the basics of it today. In particular, we will be studying the following standard classical examples: lower bound on Ramsey numbers, tournaments with the SK property, and small dominating set. Again, the emphasis of this course in probabilistic methods is on the methods. So the best way to do that is to show you examples of it in various proofs. Now, while these results are all very beautiful and nice in their own right, again, the emphasis is on learning the method by example. So let us begin with Ramsey numbers. The Ramsey number, RKL, is the minimum integer n, such that in every two coloring of the edges of Kn by colors red and blue, the names don't really matter, but we'll call them red and blue, there exists a red copy of KK or a blue copy of KL. So this is finding order in chaos, finding specific substructures, particularly nice and ordered ones. Here, monochromatic cliques. So that's the definition of the Ramsey number. Maybe most studied is the diagonal Ramsey number, where K and L are equal. And while there were upper bounds on that, in particular Ramsey was the first to prove that RKL was finite, and actually so therefore exists for all K and L, then there were upper bounds of 4 to the K around 4 to the K for Ramsey numbers, whereas Erdős in 1947 proved a lower bound, which is quite impressive. It says that if n choose k times 2 to the 1 minus k choose 2 is less than 1, then RKK is greater than n. That might not seem to give a bound immediately, but with a little bit of work on asymptotics, you can then show that for all k at least 3, this shows that RKK is greater than 2 to the k over 2 rounded down. So that is a lower bound. Again, it's still quite far from the known upper bounds, which are more on the order of 4 to the k. And this is roughly the best known lower bound. What's the proof idea, though? It is to use randomness, to use the probabilistic method. So this is one of the first and earliest examples of the probabilistic method. And what do we mean by that? We're going to take a random two-coloring. So we're going to use randomness. So we're not going to be able to kind of just construct this. What do we have to do? We have to construct the two coloring without these monochromatic cliques, but we won't actually construct it. We'll just prove that it exists using probability. So let's do that. So we will take a probability space. So here we'll take a random two coloring of Kn, where each edge is independently colored red or blue with equal probability. So half and half. So that's our probability space, and then we'll define probability events. So those are sets of outcomes. So here, for every R that's a subset of Kn of size k, we'll let AR be the event that the induced subgraph on R is monochromatic, i.e. all edges the same color, red or blue. So we have these events. What's the point of that is you can think of these as the bad events, right? We want to construct a coloring, and this would be bad. We want to avoid these monochromatic cliques, and so we'd like to avoid these so-called bad events. To do that, let's look at the probability of such one event. So for a fixed R, the probability AR is 2 times the product of the E and R choose 2 1/2. Why is that? Well, you have two colors, so that's where the first two comes from, red or blue. And then once you've decided on the color, you need each to be that color. And that happens with probability half. Those events are independent. And so we take the product and find the answer that it's 2 to the 1 minus k choose 2. So that's the probability of AR. Then we want to find out the probability kind of all events together. So we take a union bound. That is simply saying that the probability of the union of all these AR, of all of these bad events, R and V of k and choose k, is at most their sum, right? So in a probability space, the union, worst case, they're all disjoint, and so it would be the sum. So this is a nice upper bound, a useful trick, the union bound. The sum of those, of course, they all have the same probability above, doesn't depend on the R, and so therefore we can extrapolate that out and times by the size, the number of the events, which is n choose k. And now what do we know by assumption of that first part of the theorem is that this number is less than 1. So it doesn't add up to the whole probability space. What does that mean? It means that the complement of that, which is the intersection of all the complementary events, is greater than 0. In other words, with positive probability, none of the events AR occur. So with some positive, some greater than 0 chance, we avoid all of the bad events. Why is that useful? Well, those bad events were these monochromatic cliques. That means that there existed two coloring of Kn without a monochromatic Kk, thus concluding the first part of the proof. For the second statement, we need to do a bit of asymptotic analysis. So if k is greater than or equal to 3, and letting n be 2k over 2 floor, we can compute whether it actually satisfies this inequality that we need from the first part. To do that, we do some bounding. So n choose k times 2 to the 1 minus k choose 2 is at most this term on the right here, which is n to the k over k factorial. So for the first term there, I just used the upper bound, a somewhat weak upper bound on n choose k. That namely, you get n to the k over k factorial. For the other, I'm going to split it up into 2 to the 1 plus k over 2 divided by 2k squared over 2. Why do I do that? Because now when we plug in n, that n to the k becomes upper bounded by 2 to the k squared over 2, which will cancel with the lower right term, and that will leave us with 2 to the 1 plus k over 2 over k factorial. Now, k factorial should be quite a bit bigger than that, and indeed, k to the factorial is bigger than 2 to the k when k is at least 3, and so I could plug in a 2 to k on the denominator there, simplify to get 2 to the 1 minus k over 2, which is less than 1 when k is at least 3, strictly less than 1 there. And hence we get the inequality, and thus that our kk is greater than 2 to the k over 2 as desired. All right, so that is our first proof, our first example, this classic Ramsey number bound. Maybe you've seen that before. We'll move on to some remarks on it. The proof is one of the first examples of the probabilistic method, as mentioned, developed kind of in the 1940s. The proof could also be phrased in terms of counting instead of probability. What do I mean there? So you could count the number of colorings, count the ones that have monochromatic cliques. And we could phrase the entire term as counting instead of some probabilistic setup. Well, while that is nice to note, why don't we just do that? Well, one, this is a course on probabilistic methods, but also our more advanced tools that we'll learn in this class, such as the second moment method, the Lovász local lemma, and concentration inequalities, require probability to actually work. So that's one point in favor of viewing it as probability instead of counting. The second point is that probabilistic viewpoints may be more natural or intuitive than their counting counterparts. What do I mean by that? That setting it up as a probability, as some kind of random experiment, might be easier to construct. So here it might not have been clear, we should have done the counting. And this is more true in advanced problems where you might be setting up lots of different probabilities, and so the counting might seem less natural. Also, the intuition you gain from thinking of it as random experiments can also be quite helpful. So that's points on that. A point, though, against the proof is that it is non-constructive. So it only proves the existence of the coloring in the bound, but it doesn't actually construct such a coloring. So that's slightly unsatisfactory, but indeed it still does prove the result. And that's somewhat typical for some of these probabilistic results, is that they existence and non-constructive. Now sometimes you can turn them around, as we'll see maybe even in this lecture, to more constructing what is desired, but that's not always the case. Nevertheless, heuristically, when k is large, 2 to the 1 minus k over 2 is much, much less than 1, and hence a random 2 coloring of kn is very likely not to contain a monochromatic kk. So that bound we got was not only less than 1, it's much less. So with high probability, we'd actually find one of these colorings. So in that way, if we were to just randomly take a coloring somehow, we could have quite good confidence that it actually is the desired one. We don't know 100% for sure, but heuristically it would be good. So that's another thing that random proofs can provide, is they might hold with high probability, and thus confidence that if in applications one was to take them, then you would get the desired object. Now, there are examples we'll see later in this course, such as the Lovász local lemma, where the probabilities could actually be quite small and won't hold with high probability, and instead we just know that they exist if everything goes right. But here it is indeed a high probability proof. So that was our first example. We'll move on to the next one, which is on tournaments. A tournament on n players is an orientation of the edges of Kn. So what does that mean? Well, it really just oriented complete graphs. Why it's called tournament historically is because you think of it as n players, and that each of them will play a match together, and one will beat the other. So you can think of an arrow as the first player beating the second player in their respective match. And this therefore creates a tournament. Now, while that is a nice story, tournaments also are just natural objects to study in their own right as oriented complete graphs. In particular, here's one nice property that tournaments might have. A tournament T has the property Sk if for all subsets R of V of T of size k, there exists a vertex V in V of T minus R, such that VR is in ET for every R in R. What does that mean? Informally, for every set of k players, that's R, there exists another player, that's V, that beats them all. So there's always, if you fix small sets, there's always some player that beats them. So it's a certain kind of cyclic nature to the tournament, right? If you're looking at S1, it means there's always someone else beating. So there's no one who beats all. But here it's more for sets up to size k. And so that's quite nice and interesting, though it's not at all obvious that tournaments with property Sk for k large actually exist. But indeed, that's our next theorem, that if n choose k times 1 minus 2 to the minus k to the n minus k is less than 1, so some slightly different inequality here, then there is a tournament on n vertices that has the property Sk. So large enough tournaments will indeed have this property. So that's quite nice, and how we're going to do that, we won't actually, again, construct them, we will just prove their existence via the probabilistic method. And how do we do that? What's the proof idea? Is to take a random tournament. So using randomness there. So we'll take a random tournament, and indeed what we'll be showing is that with somewhat high probability, random tournaments actually have this Sk property. So let's proceed on to that. The probability space will be random tournaments on n vertices where each edge is oriented independently with equal probability, so half one direction, half the other. Again, our events here, we have to think about it, are going to be for every R subset of the vertices of the tournament of size k, we'll let AR be the event that there is no vertex that beats them all. So why are we doing that? Is because what would our bad events be? So we have to construct a tournament where every set has some vertex that beats them all, and so our bad events would be for this fixed R that there is no such vertex that beats them all. And here we want to calculate the probability of AR, but it's actually a bit harder than in the last example. So what is this probability? We have to be a bit careful. First, we can note, though, that for each vertex outside of R, it's independent, its relation to R from the other vertices, as those are different edges. And so this probability, via the independence, we can actually say it's equal to the product over those vertices of the probability that that vertex V does not beat them all. And when seen in that form, it's then easier to compute because, well, it might be hard to compute the probability that V does not beat them all. That's clearly equal to 1 minus the probability that V beats them all as their complementary events. And then that probability is easy to compute as whether V beats a particular vertex is independent. And so we get a product of half, etc., k times. So we get 2 to the minus k for the probability that V beats them all in R. And so now we can take the product of all these probabilities. We just have to do that to the size of V of t minus r, which is n minus k. And so again, here we've used this independence for that first line, and we use the size of V of t minus r being n minus k. And that should seem familiar, as that's the term that appeared in the theorem, or part of the term. Because now, as in the previous proof, we use the union bound to show that the probability of the union of all these bad events is at most their sum. They're each the same probability, and so what we get there is times the size, the number of these events, which is n choose k, and again, by assumption, we know that that is less than 1. Thus, the probability of the complement, that none of these bad events happen, is greater than 0, i.e. with positive probability, and thus with positive probability, none of the events AR occur. and thence there exists a tournament of on n vertices with the property sk as desired, concluding the proof. So again, we picked probability space, here random tournaments. We set up events. We showed that with some positive probability, none of those bad events occurred. This gives us the desired object. So another good example of the probabilistic method, another classical one. Here's some notes on this, is that we might be able to actually compute bounds. So that was only the inequality part. Like Ramsey numbers, we could also define fk to denote the minimum integer n, such that there exists a tournament on n vertices with the property sk. So finding this minimum size tournament. And then we can use asymptotic analysis, so inequalities. So here we'll use n choose k being smaller than e to the n over k to the k, which is not a terrible approximation for the binomial coefficients. And again, use this very useful inequality that 1 minus x is less than e to the minus x for all x in 0, 1. And we have that n choose k times that number is actually smaller than en over k to the k times now e to the negative n minus k over 2 to the k. So using x as 2 to the minus k there and bringing it up into the exponent. Why is that useful? Well, then you can study that and do some analysis to show that this then implies that f of k is at most on the order of k squared times 2 to the k. Why? That first term would be roughly 2 to the k squared or so, while the second term, the 2 to the k's will cancel out and you'll get roughly something like e to the negative k squared. And so this shows that around that order is when you're roughly constant. In particular, we could choose the constants correctly so as to make sure it's smaller than 1. And thus the inequality holds from our theorem, providing the tournament. And we will note historically that Sagarash proved that f of k is actually at least omega of k times 2 to the k. So while those bounds do not match, the exponential order has been determined, namely that it's around 2 to the k. So that's quite interesting in that regard. So that's our second example on tournaments. I'll turn to our third example, which will be a bit more intricate. So this is on dominating sets, a topic of study in graph theory. So a dominating set of a graph G is a set U subset of V of G, such that every vertex in V of G minus U has a neighbor in U. So what does that mean is that you have a set of vertices and everything outside has a neighbor to them. So it somewhat dominates the whole graph. That's where the dominating set comes from. And here's the nice theorem that we'll be proving, is that if G is a graph of n vertices with minimum degree delta, strictly greater than 1, then G has a dominating set of size at most n times 1 plus ln, that's the natural logarithm, delta plus 1 over delta plus 1. So why is this theorem nice? Well, of course, the whole graph, the whole set of vertices is a dominating set. So we're not interested in large ones, we're actually interested in small ones. So trying to find particularly small dominating sets would be nice. Now that's not necessarily guaranteed, as the whole graph could be an independent set, and then the only dominating set is to take all the vertices. However, if we impose some kind of condition, so here minimum degree makes a lot of sense, that you have lots of neighbors, then we could hope to get some more decent bound. Now, you can think, though, that you could just be the disjoint union of cliques of size delta plus 1, and then you could only hope for kind of a dominating set of n over delta plus 1. And here we get something rather close to that, except with this logarithmic factor of ln delta plus 1. So not too bad for what seems possible, and we'll show that it is indeed true. So what is our proof idea? Again, is to use randomness. So what should we do with randomness here? Well, we're going to take a random subset x of v of g. However, we have to be careful. If you just took kind of a random subset, it would only be of size n over 2. So we'll need to do some weighting to choose vertices only with a certain small probability. So we're going to be looking kind of to take a small random subset of x of v of g. Now, unfortunately, though, that small random subset may not be dominating. So that's the problem. We can set up this random experiment, but we might not get the outcome that we desire, a dominating set. So we're going to have to alter that a bit to fix it up. How do we do that? We're going to add the set of undominated vertices y. So if we take x, it dominates itself and all of its neighbors. Anything it does not dominate, we will add to the dominating set. And thus the result, x union y, will be a dominating set. And so our goal then is to show that the sum of these sizes x and y is indeed small enough, as in the theorem. So that's our proof idea. Do some randomness and then alter it. So let's do this. Let's do the proof. So let P, that's going to be our picking probability here, be ln delta plus 1 over delta plus 1. So that should be reminiscent from the theorem I haven't told you why we've chosen that, so we'll talk a bit at the end about where this number came from, but let's just say that that is the number. And then we'll let x be a random subset of v of g, where the randomness here is that each vertex is chosen independently with probability p. So we're picking them independently. Now I will note that why do we do it this way? Because we could also instead take all subsets of size p times the number of vertices, so all the same size, and choose one at random, and that could also work. It's just easier to analyze if somehow the choices for each vertex are independent. And so this may lead to various sets. So in particular, we could get the empty set with some probability, as they could all be not chosen, or we get all the vertices, and thus all be chosen. But the key is to kind of find the right probability to do this. And then we're going to let y be those undominated vertices. So this would be the vertices v and v of g minus x, such that n of v intersect x is the empty set, so the undominated ones. I will note that y is also a random variable, right? So x is random, and once you fixed x, then y is fixed. But since x is random, it means that y is also random. All right, so given that, now we're going to use a trick to use more probability here to calculate the expectations. So instead of just probabilities, let's calculate the expectations of these random variables. So here, instead of events and their probabilities, we have variables and their expectations. So by linearity of expectation, E of x is equal to the sum of v and v of g of the probability that v is an x, which those are each with probability p, and the sum adds up to n times p. So what is the linearity of expectation? If you have something, a random variable is the sum of other random variables, then the expectation is the sum of those expectations. And so you can view this as x is the sum, the size of x is the sum of indicator random variables for each vertex. So is this vertex in or not? So you can think of that. Now you might think, okay, it's independent, and so that works, but actually the nice part about the linearity of expectation, it works even if things are not independent. So while here these seem independent and fine, even if they weren't independent variables, we'd still be able to apply this. So anyway, we've calculated that E of x is equal to np, so it's roughly about that size, pn, at least in expectation. It's exactly. What about y? Well, let's think about what's the probability that v is in y for every vertex. Well, that's exactly the probability that v and all of its neighbors, n of v, is a subset of v of g minus x, so that aren't in x. They aren't dominated by it. So they aren't in x, and so v is not dominated by x. What is this probability? Well, written in that form, it's easier to see that it's equal to 1 minus p to the 1 plus d of v. Why? Well, every vertex has a probability 1 minus p to not be an x, and these are all independent events, so we get their product. And there are 1 plus d of v of these vertices, thus yielding that formula. Now, that depends on the vertex, of course, but we can also remember that g has minimum degree delta, and hence this is at most 1 minus p to the delta plus 1. Which provides a nice kind of uniform upper bound on all of these probabilities. With that, we can then use linearity of expectation to say that the expectation that of the size of y is the sum over the vertices of the probability v and y. Because that would be the sum of the expected amount from each vertex, which is 1 if it's in and 0 out, which is therefore the probability. And this would be, therefore, they're all the same you've got a uniform upper bound, so we can upper bound this with n times 1 minus p to the delta plus 1 as there are n vertices. So here note that we use linear expectation even where maybe these variables, these probabilities may not be independent, right? So whether a vertex is in y or not depends on whether it does interact with its neighbors, because again, this is not a random graph, it's a fixed graph. So whether my neighbor is in x or in y could be dependent. Sorry, not in y, not in x, of course. So that's a nice point to use. We've used linearity expectation again. We're going to use it a third time because I wanted to upper bound actually. I wanted to figure out the expectation of x plus y. Right? I wanted to look at we're going to have x union y as our dominating set, and so I want to think about the size of that set. And the point is, by linearity expectation, it's enough to calculate the expectation of x and the expectations of y and sum them, which we've already done. Expectation of x is np, and expectation of y is upper bounded by n 1 minus p delta plus 1. Now that's a little bit finicky to work with, so we'll upper bound that by n times p plus e to the minus p delta plus 1. So here, using a useful inequality that 1 minus p is at most e to the minus p, so that brings it into the exponent, and now we can just plug in our value of p. Recall that p was ln delta plus 1 over delta plus 1, so we get that term, and then we get plus e to the negative ln delta plus 1, because the two delta plus 1 terms will cancel. Then we can rewrite e to the negative ln delta plus 1 as 1 over delta plus 1, thus getting n times 1 plus log delta plus 1 over delta plus 1, the desired number. And then we're not quite done, but we're almost done, because the key is if we have this random variable, x plus y, and we know its expectation, there has to be some outcome that meets it. So kind of at that level and below, or at that level and above. So here we're going to use the below. There exists some x such that x plus y is at most its expectation, which is at most the desired number. And yet x union y is a dominating set by construction, and so it's a small dominating set as desired, concluding the proof. So that's the domination proof, and I just wanted to make some remarks on this. So the proof uses linearity of expectation, which we'll see in chapter 2 of Alon and Spencer. Uses it quite heavily a lot, so instead of just doing events and calculating the probabilities and avoiding those, we're using this linearity of expectation, which is quite nice. Number 2, and again, what is linearity of expectation? I said that, and again, just to repeat it, it's just if you have a random variable x, that's the sum of other random variables xi, then the expectation of x is the sum of those expectations of the xi. The proof method also uses the method of alteration. So see chapter 3 of Alon and Spencer, and we'll come back to that. But what is this? It's wherein we alter a random outcome to get the desired object. So it's not always true that you've done a random experiment and the random outcome is the object that you desire. You might have to do some modifications. So here we added y, since x might not be dominating by itself. So we took kind of a random subset, but it might not be a dominating set, so we alter it in a somewhat non-random way to get the desired outcome. So here we're adding. You could also delete vertices or change the outcome a bit, but that's the method of alteration, which is quite useful as a basic method in probabilistic methods. Finally, I'd also like to do some more notes that in actuality the proof uses an arbitrary p, and then retroactively chooses p to minimize. So I know I presented it as here's this nice value of p that works, but really you can see in the proof that we get this upper bound on the dominating set of the expectation of np plus, with our approximation, n e to the negative p delta plus 1. And using calculus, you can take the derivative of that, which is n times 1, because the derivative of p is 1, and minus delta plus 1 e to the negative p delta plus 1. Set that equal to 0, which will happen to give the minimum, and that will be 0 when p is equal to this ln delta plus 1 over delta plus 1. So really, you do the proof first, which is very typical, and then you figure out kind of retroactively what the value should be using some calculus. And here we don't have to present that as part of the proof because I just need a bound. So any p would work. We're happy to be picking the best p, but I don't have to go through that minimum analysis. I just have to be confident that it was a good choice. And so here I've showed you that. Now you could actually use the unapproximated version, 1 minus p to the delta plus 1, and change that a bit then. And that analysis might be harder. And maybe the exact formula doesn't always have a closed form minimum, and so you might want to do some approximations and then take the minimum of that approximation to get a somewhat decent bound. Also, I'll note that Alon showed that the bound is nearly optimal. So I know I suggested that maybe it could be n over delta plus 1, but actually using some random constructions you can show that this log factor is in fact necessary, and so that is pleasing, that it's roughly optimal as an outcome, as a theorem. Last, I wanted to discuss something called derandomization, which is can be seen in chapter 16 of Alon and Spencer, and that's that this proof, this algorithm, this proof can be de-randomized. So it's not really an algorithm because you're just kind of randomly sampling. You don't know, even if maybe it's with high probability this will work out. That actually we didn't even prove that, but even the proof. So the suggestion is that these can be de-randomized. What do I mean by de-randomized is actually I can strip the randomness out of this proof and there actually give you a non-random algorithm to find this small dominating set. How will that work? Well, the idea is since we kind of use the randomness to, in expectation, get this small dominating set, and we're trying to get a small one, that we could actually, instead of flipping a coin for each vertex, let's instead pick a vertex that will actually help us most to this goal of getting a small dominating set. So instead of doing it a bit randomly, instead look at among all the options and choose a non-random choice that will make the most progress and do that. So that's generally what it means to de-randomize, to somehow strip the randomize. Not all random problems can be de-randomized as such, but this one can. So let's go through that. We let x0 be empty, and we're going to do this in stages. So we'll have various xi. We'll let yi be the undominated vertices at that step. So it'll be v of g minus xi union n of xi. So what's the idea? Again, think that we haven't chosen any of x yet. So, y would be everything. And now we're going to actually choose one vertex at a time to make small dominating sets. So how will we do that? Well, in step I plus 1, let's add a vertex to xi who has the most neighbors in yi. So let's try to dominate as much of the undominated part of the graph as possible. And then we can show that actually this will make rather quick progress. So to do that, I note that if yi is r, then if you sum up all the closed neighborhoods of vertices u and yi, so closed neighborhood, that notation means u and all of its neighbors, that's at least r delta plus 1 as the minimum degree is delta. Then if you look at the average of that value over all the vertices, which would be r delta plus 1 over n, it means that there actually must be a vertex v that's in at least r delta plus 1 over n of the nu. So thus, this implies that yi plus 1 is at most 1 minus delta plus 1 over nyi. That you always dominate at least a delta plus 1 over n fraction of whatever's undominated. And then if you run this algorithm at capital T steps, where capital T is n times log delta plus 1 over delta plus 1, you'll find, with just some easy upper bounds, that this gives you an upper bound of n over delta plus 1 for y of t. And what is the size of x of t? It's, of course, t, which is n log delta plus 1 over delta plus 1, and hence xt union yt is as desired. And so you see, we ended up with xt being roughly, np, roughly what it should have been in expectation, and yt indeed be smaller, but here we de-randomized it. So the nice part about de-randomization is this algorithm isn't at all clear, or maybe intuitive, that this is what you should do, though now it seems obvious in hindsight, but it's nice because we took inspiration from the random argument, and we then de-randomized it. So we used the same setup of x and y, but instead of making kind of random choices simultaneously, we made best choices one by one, and it ended up working equally as well as the random version. Though the random, of course, easier. And this gives an algorithm. So that's de-randomization. So I really thought this proof is quite nice, and a note to end on for our first lecture, this domination proof, as it showcased linearity of expectation, which we'll return to, alteration as a method, picking kind of an arbitrary p and minimizing that and retroactively working on it, and then also this fact that it can also is a good candidate to be de-randomized as well. And we'll do some more de-randomizing along the way, but today we've covered a number of standard examples of the probabilistic method and one even more intricate one. So until next time, see you then.